Mr. Simpson here with Chapter 3, Section 4, Electronic Structure of Atoms. As always, you will see the learning objectives listed here. Please take a moment to write those in your notes. Okay, so now we're going to get into actually doing an electron configuration after talking about the quantum numbers in our last unit. So an electron configuration consists of symbols that contain three pieces of information: the quantum number, the letter designating the orbital type, and a subscript that designates the number of electrons. So you're going to see these electron configurations are going to look something like this, and we'll talk here throughout the rest of the video on how we go about doing that. Okay, so there are a couple rules that we need to be aware of that guide us in our electron configuration work. The first one is the off-ball principle. Basically, that electrons fill orbitals of lowest energy first. So a good way to help remember this is just to think about the energy levels and subshell options that we have available to us. So we said that there are 7 energy levels, and the S subshell starts right off in the first energy level and is located in every energy level. The next type of subshell is the P subshell. That shows up for the first time in the second energy level. And so basically what I'm doing here is listing all the possibilities of energy level and subshell combinations. The D subshell shows up for the first time in the third energy level. And finally the F in the fourth energy level. Now, some of those aren't possible, but that for now I'm just listing all the possibilities as we may know it. Okay, so the electrons fill orbitals of lowest energy first. So here are all our possibilities, and so what I'm going to add now are arrows which indicate the order in which we fill the energy level in subshells. So I add these diagonal arrows as I move up these possibilities. Okay, so that is the order in which they fill, and you'll see that right around here is where it gets a little different from what we may expect, in that if we just read left to right and up, actually what happens here is after we fill the 3P, we fill the 4S, and then we come back and fill the 3D. So just point out for now this location right here in the middle. I'll talk more about that in a minute. So we have the order in which the electrons fill. The other piece of information here is how many electrons can each subshell hold. So again, we have 4 different types of subshells: S, P, D, and F. They each have at least 1 or more orbitals. And so the S subshell has 1 orbital, the P has 3 orbitals, the D 5, and the F 7. And each orbital can hold a maximum of 2 electrons. So the S subshell with 1 orbital can hold 2 electrons. The P with 3 can hold 6. The D with 5 can hold 10. The F with 7 can hold 14. So if we know how many electrons each subshell can hold, and we know the order in which they fill, it's just a function at that point of counting. Let's try a couple. I have chlorine and iron here. So I've written the number of electrons present, 17 for chlorine. So I'm going to start here on my diagram, and at the bottom arrow right here. And we're going to go follow the arrows and count from 1 to 16, filling every subshell as we go. So first I'm going to fill 1s, and s can hold 2 electrons. Then comes 2s, s can hold 2 electrons. So I'm at 4, again just counting up till 17. After the 2s is 2p, p can hold 6, that gets me to 10. 3s comes next, that can hold 2. I have a total of 12. And after the 3s, I fill the 3p. Now, in the last term, we don't have to fill it. We need to get to the right number. So as I said, I have 2, 4, 10, 12. So in my last term here, I only need 5 electrons to get to 17. If you recall at the very beginning, I said that an electron configuration tells us 3 pieces of information. It tells us the principal quantum number, that's what these large numbers in front represent. It tells us the type of orbital, that's what the S and P's represent. And finally, it tells us in the form of superscript how many electrons. So that's what that information relays as I look at these electron configurations. Okay, let's try iron now, 26. Again, following the arrows. 1s2, 2s2, 2p6, 3s2, 3p6. That gets us to 18 electrons. Now, this is where I said it may be a little different. We got to make sure we follow the arrows. After 3p, if I'm following the arrows, I fill 4s. This is a function of the off-ball principle. 4s is actually lower in energy than 3d, so it fills first. Okay, so now my 4s is filled. I have 20 electrons at that point. I need 6 more. After the 4s, now comes that 3d, and I don't need to fill the d because I only need 6 more electrons. So there are other ways to depict this same information. Another one is an orbital diagram, which I've given you a skeleton of what that looks like here. So the process that I was following before, filling lowest energy first, S holds 2, P holds 6, filling the electrons before you move on, all those same rules apply. We also have to add 2 additional ones if I'm representing it with an orbital diagram. The first is Hund's rule. The lowest energy configuration for an atom with electrons with a single set of degenerate orbitals is that having the maximum number of unpaired electrons. What does that mean? It means when I get to a subshell where I have orbitals of the same energy. So looking here at an example of a p subshell. In the S subshell, I only have 1 orbital, so Hund's rule doesn't really come into effect. In the other types of subshells, I do. So now in the P subshell, I have 3 orbitals here. So Hund's rule tells us when I'm filling 3 orbitals of equal energy, I must put 1 electron in each orbital first with spins parallel before I pair them up. So I would put 1 electron in each, then I would go back and start to pair them up. That's Hund's rule. The other rule that we have to make sure that we account for here, and you see I've done it here without really talking about it, that's the Pauli exclusion principle. So the Pauli exclusion principle, which we referred to in the when we talked about quantum numbers, is that no 2 electrons have the same quantum number. It has to do with that spin factor. So when I do my orbital diagram, I need to make sure that I have if I have two electrons occupying the same orbital, I indicate one has spin up and one spin down by having, or one positive one half, one negative one half, by having those two electrons represented by these arrows pointing in opposite directions. Be aware they like to give you mistakes in orbital diagrams and ask you to pick it out, what's wrong, or what rule is it violating. So if you ever come across something like this, being able to say that's violating Hund's rule, or if you ever came across something like this, that's the Pauli exclusion principle. So off-ball principle, Hund's rule, and Pauli exclusion principle dictate how we complete these electron configurations. Okay, let me just quickly do an orbital diagram for you. We'll do phosphorus 15. If you have the space, you can do it vertically. You can also write it out horizontally. If we do it vertically, we should be increasing up the page to indicate that increasing energy. But I'll just do this one vertically. So we need 15 electrons. We're going to first fill 1s, and there's 2 electrons. Next comes 2s. Next comes 2p. And then, again, I would fill 1 electron in each before I double them up. That gets me to 10. After 2p, I fill 3s. That's 12. And then next comes 3p. I need 3 more electrons. That would look like this. Again, if your 3p was drawn like this, that would be wrong. That would be violation of Hund's rule. One other thing I'd like to point out quickly is I always put in all the orbitals at a particular subshell, regardless of if they are filled or not. So for example, let's say instead of 15, I was trying to do 14 electrons. So I would have stopped there. I'm still going to draw that orbital. That's an empty orbital. I'm still going to depict it, because if I have a p subshell, I have 3 orbitals. So even if they're not all filled, I'm going to put them in there. We're going to also look at a couple important pieces of information when we do electron configuration, and that is the number of valence electrons and also unpaired electrons. You can see here in this example that I just did, unpaired electrons are only going to happen in the last term. So even if I didn't have to draw out an entire orbital diagram, I could always just draw the last term. And I could quickly see here that I have 2 unpaired electrons. Again, this is not an unpaired electron. This is an empty orbital. With regards to valence electrons are the outermost electrons, the highest energy level occupied. So in this case, I would have 4 valence electrons. The highest occupied energy level is the 3rd energy level, 3 here and 3 here. So the 3s and the 3p, I add up all those electrons in the 3rd energy level, and I would get a total of 4. Okay, let's show electron configuration one more way, and it's a bit of a shortcut. And it comes directly from the periodic table. So the periodic table doesn't just randomly look the way it does. It's actually very specific based on a lot of different properties, but in this case we're going to talk about the electron configuration. So if I look at a periodic table, I have to think of these 2 groups over here. Change color and do that again. These 2 groups over here as the S block. Okay, and I'm going to think of this portion of the periodic table here as the P block. Okay, and then for right now, we'll just finish up with the D block, and the D block would be this location here. Okay, we said that the periodic table looks this way for a reason. As I look at these blocks that we've already discussed with electron configuration, if I think about how many electrons an S subshell holds, that answer is 2. And it's not a coincidence that the S block here has 2 groups. P can hold 6 electrons, and again, 1, 2, 3, 4, 5, 6 groups. And the D can hold 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groups. We said there's 7 energy levels. You'll notice here I have 7 periods in the periodic table. So if I can do the same thing that we were doing before with electron configuration while using the periodic table, it lends itself to being able to do a noble gas notation or shortcut. Okay, so I'm going to first do arsenic here, 33. So you can see how this works. If I wanted to do the electron configuration for arsenic right here, I'm going to start at the top of the periodic table, up here at hydrogen in period 1, and I'm going to read left to right and down until I get to the periodic table, get through the periodic table to the element I'm looking for. So as I go through a section of the periodic table, I'm going to list it: energy level, subshell, and electrons. So now, just one thing here, should really consider thinking of helium over here, because it only has 2 electrons. It's listed over here because with 2 electrons it has a filled octet, so it is a noble gas, but only has 2 electrons. So here I go. 1s2 gets me to here. Down 2s2 gets me through there. There's nothing in the middle here, nothing here to go through. So now I'm still on period 2. This is the P block, so to get through the P block, it's 2p6. Down to 3, 3s2. Again, nothing in between here, so I don't write anything until I get to, I'm still in the 3rd period, and now I'm in the P block again, 3p6 to get through there. Okay, down to 4th period, 4p2 gets me to right here. Okay, now I've reached the D block for the first time. So we have said that the D subshell shows up for the first time in the 3rd energy level. However, I'm on the 4th row here. So this is 4s that I just passed through. If I go back to where we started, you'll see that after 3p, we fill, and I follow the arrows here, we fill 4s. Then after 4s comes 3d, and then after 3d comes 4p. So sandwiched between 4s and 4p is 3d. As I go back to my periodic table, you'll see what's happening here. So the first time I get to the D block, this needs to be 3d, and it's sandwiched between 4s and 4p. So this would be 3d10 gets me to here. And finally, I'm in 4p1, 2, 3 gets me to arsenic. 4, 4p3. That's how I do an electron configuration by just using the periodic table. As I said, if I can do it that way, it sets me up to be able to do a shortcut. And that shortcut is known as the noble gas notation. Basically, the way this works is we use the noble gas in the period above the element we're looking for. So in my case of arsenic, the noble gas in the period above is argon. So what I need to do there is then just put argon in brackets. Basically what you're saying here is the first 18 electrons are the same as the noble gas argon. Those are our core electrons. Now I'm just going to go on from there. And in that case, it would be, I would then be, instead of starting up at hydrogen at 1s, I'm now starting right here. And I can go from argon, 4s2, 3d10, 4p3. So it saves me having to work through those first 18 electrons. So it is a bit of a shortcut. Okay, let's try one more and we'll do silver. Okay, silver is Ag and it has 47 electrons. So silver is located right here. So we'll do the noble gas shortcut. So again, I'll use the noble gas in the row above, which is krypton. And so when I put the symbol for krypton in brackets like that, I am saying, okay, that accounts for the first 36 electrons in silver. It has the same electron configuration. They're paired up. Their orbitals are filled in each subshell. Though that's exactly the same as the noble gas krypton. From there, I'm going to now start right here after krypton and finish. And so that would be 5s2 gets me there. Oops, sorry, I overdrew that a little bit. 5s2 gets me there. And then I'm in the D block. Again, the D's are one behind the S's. So this would be 4D, 1, 2, 3, 4, 5, 6, 7, 8, 9. 5s2, 4d9 would be the configuration for silver. Okay, two other quick things to mention here. First, there are some exceptions. And you see those two common ones here. Copper is one where, again, thinking about energy, it's actually lower in energy to fill up the 3D and have a configuration of 4s1 3d10 as opposed to 4s2 3d9. The same thing happens about halfway through the periodic table. About halfway through the periodic table with chromium, it actually is lower in energy to put one electron in each of the 5d orbitals, all with spins parallel, and one in the 4s, than it is to pair up the 4s and then leave one of the 3d orbitals empty. Just be aware if you ever see that somewhere and you think it's maybe somebody's written it wrong when they write the electron configuration for copper or chromium, there are some exceptions. Finally, predicting electron configuration of ions. So basically all we're doing here is we are adding or subtracting the appropriate number of electrons based on the charge. So for sodium +1, I'm not doing an electron configuration of 11 electrons, I'm doing it of 10 electrons. Phosphorus 3- means I've gained 3 electrons, so instead of the 15 that phosphorus would have, I'd be doing a configuration for 18, and so forth. And you can see here are those examples that I'm talking about. So again, we did 10 electrons for sodium cation, and we did 18 electrons for the phosphorus anion. Okay, that's it for this section.